Good evening and welcome to the first LATES event of Be Curious Live in 2021. My name is René Oudmeijer. I'm the head of astrophysics here at the University of Leeds, and I'll be a host for the next hour or so. The Be Curious event is basically our annual showcase of the Leeds University research, and we tell the world about everything that we're doing. Today was the first day already, time flies, and we continue having family events at 4 p.m. in the afternoon and late events at 8 p.m. all the way up until the 15th of July. Every single piece of research that is being done in Leeds will be showcased here. And it might be a coincidence or not, but tonight we start with an A, astrophysics. We're here in the astrophysics group, and what we'd like to tell you about is the research that we're doing. We've done it in such a way, we've got 3 of our researchers, each telling a bit of their research, and it all has to do with the big questions that we have. And the big question for tonight that we want to discuss with you is, where do we come from? How was Earth made? Are worlds habitable? Okay, and our first speaker is one of our PhD students who will be talking about how stars form. The second speaker is one of our lecturers who is going to tell you about the disks that actually form around these stars, and in these disks, planets can form. Well, our final speaker, he's also a PhD student, is going to tell you about the planets that form in these disks and how we can find out that life might or might not exist on them. Okay? If you've got any questions, please ask them, and you can go to the right on your screen in YouTube and type them in the chat. If you have questions during the talk, please put them already in the chat. Don't worry about it, because then we've got some questions already to choose from. Now then, our very first speaker is Martin Koupelas, and I would say, Martin, the floor is yours. And everybody enjoy.
Okay. Hello. My name is Martin, and if it would be possible to get my presentation on screen, there we are. Fantastic, brilliant. Welcome everyone. Like I said, I'm Martin, and I'm an astrophysics PhD student here at Leeds. And this is the first talk of the 3-talk series that's going to attempt to tackle some of the problems associated with the question, what needs to happen in order to create a habitable world? How do you create a habitable world? And yes, my presentation will focus a little bit on star formation. So I'll just give you an overview of what to expect in this talk. And yes, please feel free to ask any questions during the talk and afterwards about anything that's been said here. So first, I'll talk a little bit about what do we actually mean by the word habitat. What do we then mean by something to be habitable as well, and what are the ingredients that are needed to say if you want to make a habitat from scratch, for example. And then I'll talk about star formation and the relationship of star formation with the interstellar medium. And then finally, I will highlight some of the work that I've done here as part of my PhD here at Leeds. Okay, so if we just wipe the slate clean for a second and think about what it means for something to be a habitat, specifically what it means for something to be habitable. I'm not sure what pops into people's heads when they think of the word habitat, but what I think of the word habitat, I think of my bedroom here at Leeds. So you can see that it's got quite a nice view of the city centre and a nice telescope to do some astronomy research. But that aside, if we know from our experience of bedrooms, even ones with an infinity pool, that if that was it would be something peculiar. You couldn't just put a human being inside one of these things, although it'd be nice for a couple of days. Very quickly we'd realize that, okay, we're getting a little bit hungry, we want some food, so we need some source of energy to sustain us, otherwise we wouldn't be able to sustain an 80-year lifespan if we are located in one of these things alone. So we know that we need some source of energy to give us food, we need some source of energy to provide power to power our home, and then we need some sort of process to remove any waste energy from our habitats. And then basically our bedrooms are embedded in this wider system which can support human life. So I would say that what it means for something to be a habitat and for something to be habitable, it means that it can sustain life, which is what we're here to talk about. And so we run into a lot of problems when we start to think about it and keep zooming out and zooming out. But luckily for us, Carl Sagan simplified things a lot back in the day when he talked about how to create an apple pie. And to make an apple pie is really not too different to making a bedroom like this. And really what we need is to create a universe. So at least we have a starting point, and we can basically work along this path from starting a universe, from creating a universe to creating a bedroom and starting to answer some of these questions. So if we just think a little bit about what populates this top of this arrow, well, we can start from thinking about the bedroom again. We know the bedroom needs to be part of a building usually, and then that building needs to sit on some land. So we need to get some land. Where else better to look for some land than on a planet? So once we have a planet, we can't really stop right there, because in order to get a planet, we need a star, and to get a star, you need something to create the star, which is inside a galaxy. And yes, throughout all three talks, all different stages of this arrow will be talked about. But I'm just going to focus on this subsection of the arrow right here. Now, this subsection actually decomposes into two arrows, and what this actually represents is quite a broad cycle. And this is a cycle of material and energy that occurs within the galaxy between the interstellar medium and the stars. So the image goes like this. Stars form out of the interstellar medium, and then the interstellar medium is subsequently affected by the presence of stars, which then affects the future generations of stars. So really, star formation, as taught in GCSE textbooks, where we see this kind of big ball of material, that's where we have the competing forces of gravity and pressure, where gravity starts to win and the material collapses to form a star, is actually part of this much broader process which drives the evolution of the galaxy. Okay, so if we just want to make it come alive a little bit in our heads, we can take a look at some images of the galaxy. So this is a very nice optical image. So this is an image taken in the visible range of the electromagnetic spectrum. So this is the light that our eyes are most familiar with. And we can see a lot of bright and kind of glowing regions, which basically shows the effects of stars. We see starlight in those bright regions. And then the dark regions where starlight gets obscured and absorbed are actually the dense molecular regions where a lot of star formation is taking place and a lot of the massive stars are embedded in. And so while this is quite a nice image, we don't see everything because visible light gets absorbed pretty quickly. And so we can actually image the galaxy in a whole host of different wavelengths along the electromagnetic spectrum, which can tell you a lot about the components of the galaxy and where star formation is taking place and the dynamics of what's going on. So if we look at the top, for example, we see a lot of cold regions mapped out in dust and carbon monoxide. So carbon monoxide is actually mapping out the molecular clouds, which is where stars are forming. And then dust is also mapping those out, but it's also showing the currents within the galaxy as dust can kind of swirl around with the material that's being pushed around by stars, by stellar winds from stars and the radiation, and also how it couples to the magnetic field. So looking at the bottom, we see some of the emission exotically named free and synchrotron, which shows us some of the activity around the really hot plasma, where again, for example, in the synchrotron, you can see how it couples to the magnetic field. So we can see some of the broader activity in the interstellar medium that's happening at the same time as star formation. So while it's helpful to consider star formation as something that takes us from this to this, in reality, what's actually happening is something that looks a little bit more like this. So it's a very, very messy picture where you see stars forming in clusters, massive clusters of hundreds and thousands of stars, which then disrupt the surroundings around them. And then the surroundings around them change and evolve. And from that material, new molecular clouds are formed, and then new clusters of stars are forming. So we can be a little bit forgiven if we're puzzled as to how in the world something like that can produce anything that's habitable, but it does. So it's quite a miracle, really. But we'll talk a little bit more about how that happens in some of the other talks in the night. So I'm just going to present a little bit on some of the research that I've done here as part of my PhD. So for anybody unfamiliar with the process of science and research and how research operates, basically researchers publish their findings in scientific papers, which get disseminated all over the world in journals, and every researcher has access to these pieces of work, and that's how information propagates in science, and that's how we can do science. So in this piece of research, I basically look at the formation of a molecular cloud prior to star formation, and out of atomic diffuse interstellar medium. So the cloud evolves due to some physical processes which cause it to form a clumpy medium, as we can see over here. See if I can get this laser pointer. Here in panel A, we have a very inhomogeneous cloud, and you can see some of the signatures here just from a shock that's basically come in from an external star somewhere over here, let's say, and it's impacted the cloud, and that causes a lot of interesting dynamics inside the cloud. And then ultimately, after a period of about 5 million years, the cloud loses its identity that was seen at the start, and some material inside it collapses under gravity. And so this piece of work basically showed that here's a possible scenario where you take material that evolves due to some physical processes that has the potential to form stars. So that's good. And I'm basically going to end a little bit here with an image that when I saw first kind of blew my mind a little bit, and answered some of the questions as how is it that in such a crazy interstellar medium like the one within our galaxy, we can actually sustain life on a planet like ours. And this is what you're looking at here is something called the heliosphere, and it's where the solar wind interacts with the interstellar wind, basically creating this protective bubble around all the material around us. So it makes it a little bit easier for life to happen on the planet that we're on. And so I'll again end here and take any questions.
Thank you very much for a very nice talk. There was one question actually that popped up the other day, and perhaps some of the people in the audience may have the same question. If you've got any questions, please put them in the chat. But how quickly does a star form? Does it take billions of years, or how does that work?
That's a very good question. I'm not entirely sure how old the stars form, because the stars form in all shapes and sizes and masses. You know, you can get stars that are like a fraction of the mass of the sun, and then stars which are 50, 100, 200 times the mass of the sun. And so they all form at different timescales. But I think the rough timescale with the stars that I'm most familiar with working takes less than about 1 million years for basically the material to assemble and collapse to form a star. But of course, it depends how far back you look at, because if you're thinking about the formation process of the accumulation of the first clumps and the cores that can collapse down to form stars, that can happen on near the lifetimes of the clouds themselves. So we can look at things that take about 5 to 10 million years, or up to 15 million years.
So perhaps I should tell the audience that 1 million years might seem like a lot, but if you consider that our own star, I think, is already 5 billion years old. That's a very short pregnancy indeed, right? 1 million years over 5 billion. That's very quick.
Indeed.
There was another question that came up. You mentioned interstellar medium. So and you mentioned dust. So where does that come from, the interstellar medium?
That's a very good question, because that's a very puzzling question, because I mean the interstellar medium, really a lot of the interstellar medium comes from the material that is ejected from stars themselves, but the stars have to come from somewhere. So it's quite a question of where does the interstellar medium come from really is kind of edging on the question on how did our galaxy form, and because, you know, a lot of material comes together because of gravity, and then any inhomogeneities inside the material that has that basically were there from early stages of galactic formation, that would then be the pockets where the stars form, and from that on the interstellar medium evolves from that. So again, it's part of a much bigger evolutionary cycle So it didn't just appear out of nowhere, just like stars didn't appear, but it was part of this assembly that basically brought the galaxy and the interstellar medium and the stars together.
That's fantastic. So indeed, so the hydrogen and the helium from which most stars are formed, and they make all these new elements, and they, as you said, ejected into the interstellar medium. So it's actually quite a circle of life already.
Absolutely, absolutely, yeah.
I believe we've got one final question, and then we could move on to the next speaker. Can magnetic fields help or hinder star formation?
I know that in the process of cloud formation, it can really affect the timescales on how the structures within the clouds themselves evolve. So I'm not entirely sure how magnetic fields affect the final collapse of the clumps, but in terms of cloud formation, it can really kind of suppress some of the dynamical effects that might be there. For example, if a shock comes along and tries to disturb the material, the magnetic fields can kind of keep the material held together for a little bit longer. So it might actually delay star formation. And in terms of increasing star formation, again, any material that is flowing due to magnetic fields in the clouds can interact sooner and can be held together and compressed, and therefore can collapse faster. So it can really have both of an effect. Usually we find that these things kind of do both. Is like shocks can trigger star formation, but shocks can also inhibit star formation by blasting material away.
Okay, so life stays complicated.
Life stays complicated.
Let me just tell the audience, so after the three talks, there will be plenty of time for questions as well, so please do not hesitate to put any questions for Martin in the chat later on if you want. So thank you very much, Martin. Our next speaker takes it in the next step of our story, going from stars to the disks around the stars and the planets. Dr. Katharine Walsh will talk you through that. Over to you, Katharine.
Thank you very much, René, and thank you so much also to Martin for that lovely introduction into the interstellar medium, so this place that we have between the stars where stars can form. So it's my great pleasure to tell you all about my own research area, and that is investigating how planets form. And to start, let me show you one very detailed view of the outcome of planet formation that we have, and that's, of course, our own solar system. So you'll see in this artist's impression what our solar system looks like. We have the four inner rocky planets closest to the Sun: Mercury, Venus, Earth, and Mars. Then we have the asteroid belt. And you can think about this as kind of the stuff left over, the stuff that didn't quite make it into planets. Then beyond the asteroid belt, we have the giant planets, the two gas giants, Jupiter and Saturn, followed by the two ice giants, Uranus and Neptune. And all four of these giant planets are mainly made out of gas and have no real solid surface, unlike the rocky planets, one of which, of course, we live on. So as Martin mentioned, we kind of assume that life prefers to live on a rocky planet rather than one of these gas giant planets. So also surrounding the solar system, we have this large reservoir of icy bodies. And this is a source of comets that occasionally pop in to the inner solar system and pay us a visit, where they're warmed up by the sun and we see kind of the beautiful coma that they generate. So you can see from this image that the planets in our solar system orbit in a plane that is at right angles to the rotational axis of the sun. And this already gives us a pretty good hint as to the origin of our solar system. So what you're seeing now in this artist's impression is an imagining of the raw material used for building planets. What we have is a rotating disk of dust, gas, and ice that's orbiting a newly born star in the center. And this is what we call the Protoplanetary Disk. What hopefully you can also see is we have a very clear boundary in this image. And what this boundary is, this is what we call the snow line. Within the snow line, we only have dust and gas, whereas beyond the snow line, we have ice. And this gives a clue, hopefully, to why our solar system looks the way it does. Inside the snow line, we only form rocky planets, like the Earth, whereas beyond the snow line, we have enough solid material to form the massive cores that we need to then form giant planets like Jupiter. So where does this protoplanetary disk come from? Well, kind of as Martin had hinted at, they arise naturally during the process of star formation. So here's a little video just talking you through, they're showing you what happens. So we have a shock wave passing through a molecular cloud in the interstellar medium. And at this point, gravity really takes over the evolution of the cloud. It starts to collapse under the force of gravity. As it collapses, it spins up, very similar to how an ice skater that's spinning on the ice, when they bring their arms in, they also speed up. And because the collapsing material is mainly gas, it also spreads out, very similar to when you rotate the pizza dough to create your pizza base for making your pizza. And it's actually within this spinning disk that then dust particles begin to collide and stick together, some of them eventually growing big enough to grab a hold of that gas to build a gas giant planet. So we can imagine, as shown in the video, that as the planets are forming, they clear the material in their orbit, creating rings and gaps in the disk. So everything I've shown you so far has been a little bit of an artist's impression and imagining, if you like, of what we think this process happens. So can we actually see this process happening around nearby young stars? So what I'm showing you here is an image at visible wavelength light, so the wavelengths at which we see the world. And this is of a star-forming region called HL Tau. And if we zoom into this very bright region in the center, and we zoom in using wavelengths much longer than visible wavelength light, at millimeter wavelengths, then this is what we see. So what you're looking at is light coming from the coal dust orbiting in a disk around a very young star. And you can see that this dust appears to be sculpted into rings and gaps, very, very similar to the final frame of that video that we all saw. So one explanation for these structures is that the gaps are actually caused by forming planets. So the forming planets are sweeping up the dust in their orbit, and the bright rings then correspond to an accumulation of dust that may then go on to form a next generation of planets. To give you a sense of scale in this image, on the right you'll see the size of the solar system with the orbit of Neptune highlighted. So we're really peering very, very deep within this new planetary system into the region where planets are actively forming. So how do we make these very detailed observations of planetary systems? Well, we and all my collaborators and colleagues, we use state-of-the-art telescopes. And in particular, we use this one called the Atacama Large Millimeter Submillimeter Array. That's a bit of a mouthful, so we call this telescope ALMA for short. And ALMA is an array of 66 radio telescopes in the Atacama Desert in Chile. And these are combined together to act as one big giant telescope with a dish size of up to 16 kilometers, so really massive. And ALMA has been designed to make very, very detailed images of the dust and gas in the universe, including in star and planet-forming regions. So I showed you the image of HL Tau with its beautiful dust rings revealing the presence of forming planets. And one question that you might have is, how common are these structures, and do we expect to find them around all young stars? So here you'll see an array of several more ALMA images of, again, the coal dust in disks around nearby stars. And you can see that these show remarkable diversity. You'll also notice that rings are actually very, very common. Sometimes these are very well defined, sometimes they're a little bit more diffuse and spread out, but we also see other effects like spirals and clumps. Features, again, we think are caused by forming planets. So we now know that these young stars are actively forming planets, and we can make a prediction. We can predict that this diversity in structures that we see could arise in many different types of planetary systems. That is, we might not expect all planetary systems to look like our own. And Greg, who's talking later, will tell you a little bit about those planetary systems. The other thing is that everything I've shown you so far has given us very indirect evidence of forming planets. We kind of see the influence of the planet on the disk rather than seeing the planets directly. So can we actually see the planets themselves? Astronomers are trying really, really hard to do this, but it's very, very difficult because the planets are so tiny and faint compared to the star and the disk. But one way to try to reveal a location of the planet is to look at what the planet also does to the gas. So here's an image of the coal dust rings around this star, HD 97048. And what we can do with ALMA is we can look at the speed of the gas as it's orbiting the star. And what astronomers have found is that they can pinpoint the location of the planet because it causes a little kink in the gas speed as the planet's strong gravity sucks up the gas like a hoover, if you like, or a whirlpool from the disk. And this is really, really strong evidence for a forming planet because this kink also coincides with a dust gap, again, presumably carved out by that forming planet. So despite this very, very strong evidence, it's still indirect evidence for the planet. We're still looking at the effect that the planet has on the disk. So again, have we been able to directly image a forming planet? And the answer to that is yes, we have, at least in this one system, PDS-70. So this is a visible wavelength light image of the disk around a young star, revealing really compelling evidence of multiple planets. So you'll see the blob in the bottom region there, and also this extension of emission from the inner edge of the disk. So we think that there's potentially 2 planets in this system. So astronomers went back and they looked at the system again using an instrument that can see hot gas, but also using ALMA to reveal the coal dust. And all 3 data sets combined together really reveal the presence of these 2 baby planets. PDS-70b, you can see there, which is the blob, PDS-70c, which is sitting at the inner edge of the disk. So we can see these planets directly because as the planet sucks up gas from the disk, the gas is heated and emits light at a very particular wavelength that we can then pick up with large telescopes like the VLT. So yes, indeed, we can see planetary systems in the act of formation. And what we're finding out is that planet formation appears to be a universal byproduct of star formation. And we see a huge diversity in the structures that, again, are likely to lead to a huge diversity in planetary systems. But what other information can help us determine the habitability of these young planets? Well, not only can we detect light from coal dust with ALMA, we can also tune ALMA to very specific wavelengths to pick up signals coming from specific molecules. So we can use ALMA to look for, in particular, life-friendly molecules that contain carbon, oxygen, and nitrogen, all those elements that are very important for life. So here you see an image of the coal dust, again, in these beautiful rings around another young star, HD 163296. And myself and my collaborators looked at this young star also at very specific wavelengths to look for molecules and measure the composition of the gas. And what you can see in this image overlaid is the emission or light coming from one molecule, hydrogen cyanide. It's an important molecule actually for the making of amino acids. And just like the dust, you can see that the light from the hydrogen cyanide is present in rings, showing us that the abundance and distribution of these key ingredients are also affected potentially by the presence of forming planets. So my collaborators and I have looked at these disks and many different carbon-bearing molecules that together reveal the composition of this planet-building material. So in the various different rows in this array, you can see 5 different protoplanetary disks, and every single column in this array is a different molecule, a different carbon-bearing molecule. So one way we analyze this data is to compare with the solar system, in particular with the information that we have preserved in comets. And what we're finding is that we find the same ingredients around these young stars as our solar system had before our planets formed. So it does appear that other planetary systems have key ingredients needed to kickstart life on their rocky planets. So just to finish, what have we learned in this crash course on planet formation in the past 10 minutes? So we've learned that planets form in these disks of dust and gas that arise around new stars, and that planet formation and star formation go hand in hand. We've also seen that we can see signatures of planets forming in these disks through the rings and gaps that they carve in the dust and the gas, but also in the gas kinks that we can see as the planets are pulling the gas onto themselves from the disk. We've had one very famous system, PDS-70, where we've been able to directly image 2 baby planets forming in that planetary system. And finally, I've shown you how we're using ALMA to see light coming from life-friendly molecules in the regions where planets are forming, showing us that the ingredients needed to seed life on our planet are also present around other stars. And on that note, I'll say thank you, and I'm very happy to take any questions.
Thank you very much, Katharine, for a wonderful talk. And it's amazing, these new images that they're very recent. And even 20 years ago, the telescopes were only good enough to reveal a blob rather than these beautiful structures that we see. We've got some questions here. Isabella was asking, and I think there's a theme in some of the questions. I think people are fascinated by the idea that we actually get a disk around a star. Isabella says, why does a disk form around a star instead of a ball of gas surrounding it in all directions? So why do we get this disk?
So that's a very good question. And it comes down again to the balance of forces that are acting on this ball of gas as it's collapsing. So as I mentioned, as the gas is collapsing, it's spinning up, right? And it's spinning up in the perpendicular to the axis of rotation. And what happens is that if you've ever put a ball on a chain and swung it around, you'll notice that there's a force acting opposite to the direction towards the axis, right? So you'll feel a force on your hand as you spin the ball. So that's the centrifugal force, and that's acting in the opposite direction in the equatorial plane, which is perpendicular to the axis of rotation. So hopefully you can imagine that. And that centrifugal force is just enough to kind of stop the infall of material along the equatorial plane, but material coming down through the poles can still fall onto the disk. And that's why you end up with this flattened structure. So it's kind of a consequence of gravitational collapse and rotation and the balance between the force due to gravity acting inwards and the centrifugal force acting outwards, which is maximum in the plane of the disk.
Fantastic. So yeah, that's the same force, of course, that makes our clothes dry in a washing machine, right? Because
exactly.
So there you go, dry clothes and getting disks, same thing. Got another question. Again, the disk. So do the largest disks form around the largest stars and the smallest disks around the smallest stars? Or is that
That's an excellent question. And Martin told you that stars come in all shapes and sizes. Well, not shapes, they're all about the same shape. But they come in all different masses and sizes. And our sun is a G-type star and is one solar mass, of course. But we have stars that are a tenth of a solar mass all the way up to hundreds of solar masses. So it's very interesting, actually. So we do see, in stars around which we detect disks, we do see actually a relationship between star mass and disk mass. Okay, so the larger the mass of the star, you tend to form a more massive disk, and that's probably because you started off with more material in the core that then eventually collapsed. But there's, at some mass point, you're going to actually build a more massive star. And then, so this is what we call like O-type, B-type stars. And at that point, actually, the radiation from the star itself starts to, what shall we say, disrupt the formation of the disk. So whilst the system wants to form a disk, you've got very, very strong radiation coming from these very massive bright stars that, again, acts opposite to the force due to gravity and starts to disrupt the formation of the disk. But there's been a lot of very interesting results recently that shows that, at least for a short period of time in these massive stars, they do appear to have a disk. They're just very, very difficult to see because they only exist for a very short period of time. So we have to make our observations at just the right time to see them. So certainly, I think that the star formation and planet formation community, we're kind of agreed that disks play a role, that they form around possibly most types of stars, except maybe the very most massive. And indeed, we expect much more massive disks around more massive stars.
Fantastic, thank you. Final question then at the moment. This is a follow-on really on the first question. You mentioned that, that this collapsing material spins faster, but why does it begin to spin? Is basically the question. Was it spinning already, or was it stable, and why?
Really good question. It all came from the emergence of the universe. Everything that exists now was injected into the matter that has come together to form stars and planets. at the birth of the universe. So there's lots of motion and movement just intrinsic within galaxies because of that, that birth of the universe. And then there's lots of, like Martin was saying, I think there's a lot of energy also injected into the interstellar medium by these massive stars. Like if a supernova goes off nearby, you're going to get a big blast of a shock wave that will come through and help to inject rotation and momentum into gas. So everything is moving relative to each other. So everything has a bit of angular momentum left over from the emergence of the universe, and then you can get little pushes and little extra energy injections through, being close to these energetic events like supernova. So that's where kind of the rotation comes from, and it's rotating really, really slowly. Much slow. I think I worked out that for a typical molecular cloud, for it to complete one full rotation is like 100,000 times the age of the universe, right? They're moving really slowly, but you're collapsing over 20 orders of magnitude in density, and I think about 6 or 7 orders of magnitude in size. So that really, really spins up when you're going over those massive size scales.
So there you go. Thank you. So we do need a little bit of maths for astrophysics as well.
We do.
So fantastic. Thank you very much, Katharine, for your presentation. Let's move on to the final talk. Let's see what kind of planets we have and whether they're habitable or not. I'd like to invite PhD student Greg Cooke to tell us everything about it. Over to you.
Good evening, everybody. So yeah, I hope you enjoyed Katharine and Martin's talks. I know it's late, I know it's a Monday, but please stay with me. Please don't fall asleep just yet. So yeah, my name's Greg. I'm a second year PhD student and I study planetary atmospheres. In my talk, I will be discussing what makes a planet habitable. So first of all, I want to talk about how many planets there are out there in the universe. So we know of the 8 planets in our solar system, from Mercury, which is closest to the sun, through to Earth, the gas giants, and finally Neptune, the furthest away. But what about outside the solar system, around other stars? Well, an exoplanet is a planet that orbits a star that is not the sun. So you think of any of the billions and billions of stars out there, if it has a planet, then that planet is known as an exoplanet. Astronomers have actually discovered more than 4,000 exoplanets so far in our galaxy in just 25 years. And we've calculated that there's at least 1 planet per star, and maybe more than that. And that means that given all the stars in the universe, estimates suggest there are more exoplanets out there in space than grains of sand on Earth. So if you've ever been to a beach or a desert before, you might find that really surprising. Just let that sink in. More exoplanets out there in the universe than grains of sand on Earth. Okay, so you might be sat there thinking, what do we mean by habitable in this sense for a planet? Well, essentially, habitability is a measure of how suitable an environment is for life. To give an example, many places on the Earth are habitable, but Saturn is not considered habitable because it's too cold, there's not really a surface, and the atmospheric pressure is very high. And that's the first major point. Our understanding of habitability is based on what we know about life on Earth. So we don't really have examples of life elsewhere, and Earth is really just the best starting point for defining what is habitable and what is not. At the basic level, the definition of habitability depends on the temperature. Is the planet too hot or too cold? Or is it just right? Is there a reliable energy source, such as sunlight or heat coming from the planet's interior? How available key molecules are? Does life have access to the molecules it needs to survive and reproduce? So liquid water is really a key player when considering the habitability of any planet or environment. It's essential for our well-being. We all know it. We need to drink it every day to survive and feel good. It's also essential for all life on Earth. Some life forms, like a cacti in the desert, need only a little bit, and others need a lot, like humans and dogs. Generally, where there is water on Earth, there is life. We haven't yet found a life form that doesn't require at least some water to survive. So, this commonality puts a great importance on liquid water when astronomers try to define if a planet is habitable or not. And that brings us nicely to the concept of the habitable zone. This is the region of space around a star in which liquid water could exist on the surface of the planet indefinitely in order to support life. If the planet is too close to the star in the red region, then the water boils away into steam. If the planet is too far away, as in the blue region, then the water freezes into ice. In the green region, the planet can comfortably sustain liquid water. Of course, on Earth, we have all three forms. We have water vapor, liquid water, and ice. But the important point is we have a huge abundance of permanent liquid water in the oceans, lakes, and rivers. Now, water needs to be kept under sufficient pressure at a certain temperature to remain liquid. Fortunately for us, on Earth, our atmosphere provides the necessary pressure, and it also traps enough extra heat from the sun to keep the water in the oceans from freezing. The atmosphere also provides important gases for life, such as oxygen, nitrous oxide, methane, and carbon dioxide, as well as many more gas molecules. The atmosphere protects us from damaging solar radiation, such as X-rays at the top of the atmosphere, and also in the ozone layer, several kilometers above our heads, the ozone layer absorbs ultraviolet radiation, which would actually make our sunburns even worse than they already are if that ozone wasn't there. Now, for these reasons, if a planet doesn't have an atmosphere, then living on the surface would be much more challenging. So my research is mainly focused on the atmosphere of Earth and how this may apply to exoplanets that are similar to Earth. So at the moment, I'm researching Earth's past, in particular the last 2.4 billion years, where the Earth went from having virtually no oxygen in the atmosphere at all to a rise in oxygen and then the oxygen-rich atmosphere we need in order to breathe today. To do this, I've been using a climate model that is usually used to simulate future climate change, but instead I've applied this model to Earth's past climates. So all of this begs the question, do all planets need to be Earth-like if they're to be considered habitable? Not at all. They could actually be larger or smaller. So many exoplanets over a range of sizes are expected to have a rocky surface. If they're in the habitable zone, then they might have liquid water too. They could have vast oceans under an ice sheet, just like the icy moon Enceladus in our solar system, pictured here. They could orbit hotter or cooler stars. If they orbit hotter and more luminous stars, then to remain habitable, they need to be further away from their host star. The opposite is true for cooler stars, where the planets need to be much closer in to the star in order not to freeze over. If a planet orbits one of these smaller, cooler stars, then they're expected to be tidally locked, which means that they spin at the same rate they orbit, and that gives them a permanent day side and night side, where the day side will be much hotter than the night side because it always sees the sun, and the night side never sees the sun. And a habitable, tidally locked planet would need to maintain liquid water at some point on the planet, but not all over the planet. Now, there are several planetary systems out there of interest, and perhaps the most interesting in terms of potential habitability of its planets is known as Trappist I, which has 7 roughly Earth-sized planets orbiting around it. Each planet is labelled with a letter, with planet B closest to the star and planet H furthest away. The star is much cooler and redder than the sun, and as such, all the planets orbit much closer to Trappist I than Mercury orbits the sun, as this diagram shows. Each planet is likely to be tidally locked, as I mentioned on the previous slide, where the sun in the sky will never set or rise on these planets. And in fact, this planetary system is so popular that NASA even made a poster about Trappist I, which is the 4th planet from the star. It's in the habitable zone, it's 90% the size of Earth, and it could support liquid oceans. There are some other interesting candidates too. Star Wars fans will know the fictional planet Tatooine, which has 2 stars in its sky, just like the actual planet Kepler 16b. As different stars have a peak brightness which is at different wavelengths of light, some planets might have vegetation that is a different color to green in order to maximize photosynthesis. So a planet like Kepler 186f, which has a very red star, it might have blue or yellow or green or red vegetation. We don't really know, it's all hypothetical, and that's the problem at the moment. We don't know what the surfaces of these planets will be like and what they'll look like. In total, we have around 20 and possibly up to 60 potentially habitable exoplanets that we know about so far. So indicated in the diagram, we have some solar system planets for size comparison with all of the current best 20 habitable candidates out there. And each of them are potentially habitable because they reside in their star's habitable zone and they're probably a rocky planet. But all of these exoplanet pictures are just artists' impressions, unfortunately. So far, astronomers actually know very little about these exoplanets. We need more information to accurately characterize them and determine if life could live on these worlds. And it all boils down to this current picture of only knowing a few simple facts for most rocky exoplanets. So for the star, we might actually know the temperature, the mass, and the size of the star, but we might not know its age. For the planet itself, we'll probably know the size, and for about 20% of planets, We actually know their masses. And we probably also know the orbital separation between the star and the planet. But in terms of the chemistry of the planet, not just of the rocks and geology, but also of the atmosphere, and in terms of the surface, there are big question marks over this because we really don't have any idea yet. And that's because the current set of telescopes we use are too small and they don't have the required sensitivity needed to see these exoplanets in enough detail. So we just need bigger and better telescopes. Fortunately, construction is underway on some larger and more sensitive telescopes, such as the European Extremely Large Telescope, yes, that is its real name, pictured here on the left, and the James Webb Space Telescope, pictured here on the right-hand side. Now, generally, ground-based telescopes like the European Extremely Large Telescope can be built bigger and cheaper, and they are much easier to upgrade and repair, but they suffer from viewing exoplanets through our own atmosphere, which can be cloudy and light polluted. Now, space-based telescopes, on the other hand, do not suffer from observing through our own atmosphere, but putting them in space is much more expensive, challenging, and risky. Now, in the next few decades, there are plans to observe some of these potentially habitable exoplanets with the most powerful telescopes ever built. And that's really exciting, but it's only half the challenge. Determining whether a planet is habitable is one thing. All that means is whether or not life could live there. But does life live on any exoplanets? And how would we know? What exactly are we looking for? I'm not necessarily talking about super intelligent life like you see in the movies, but generally life of any kind, and in particular simple life like bacteria, which evolved long before humans did billions of years ago. Astronomers will look to see, are the surface temperatures habitable? Does the planet have water, and is it likely to be liquid? Are there any gases present that indicate life in an atmosphere? And what sort of gases are there? If there's oxygen and methane, that might indicate that life could be working away, breathing and respiring on the surface or in the oceans. And there's also the possibility of technosignatures. These are a bit more speculative, but could aliens be watching their own form of TV or browsing YouTube? Who knows? We're not sure yet, and we won't know until we start looking with these bigger telescopes. It would be great to just point one of these bigger telescopes at a planet and say, hey, look at this amazing planet. Isn't that nice? Wouldn't we like to live there? But it's not looking like this. The actual current picture of rocky exoplanets looks like this pixelated image on the right-hand side. And that's the best we can do so far. And it's only a few pixels, but fortunately, we can actually do some great science with those few pixels. Now, in the next few decades, we'll potentially discover and characterize many habitable worlds out there. And I have no doubt that there'll be some amazing surprises along the way. And I'm really looking forward to those moments of discovery. Thank you so much for listening.
Greg, thank you very much for your talk on life on other planets. And sometimes people are even doubting whether there's intelligent life on Earth, but that's a different topic altogether. So I've got some questions in the chat for you. And I also found some questions that perhaps we can do afterwards to all of the speakers today. The first one is from Emma, and she asked, are there any other planets in the solar system where we might find life?
Yeah, so there's been a lot of talk about Mars for many years because it's a rocky planet, and even though it doesn't have much of an atmosphere, some people have wondered, could life be living under the surface somehow? And we haven't found anything there yet. And then recently, last year, there was a controversial possible detection of life on Venus, but no one's really sure about that. I think some of the more interesting candidates are actually moons, and you've got moons of Saturn, which are Enceladus and Titan, and there's also an icy moon called Europa that orbits Jupiter. And for Enceladus and Europa, you have liquid water oceans under thick sheets of ice, and we're not really sure yet if life could live in the water there. Perhaps it's too difficult for life to originate, but there's some missions coming up in the next few years that are going to explore that. And then Titan has some interesting chemistry. It has lots of hydrocarbons, and some people wonder if that would be a suitable environment for life to form. Instead of liquid water oceans, they have sort of methane that rises and falls and makes methane clouds and then rains onto the surface into liquid methane rivers and lakes. So there could be life on planets in our solar system. It wouldn't surprise me if we found some, especially in Enceladus and Europa, because of those liquid water oceans. But yeah, I think Venus and Mars are much more tentative at this stage.
Okay. Fantastic. Well, actually, the next question was linked to the first question, and you almost alluded to it as well, because you mentioned rightly so that astronomers are mostly interested in liquid water for life. But a fair question is indeed, as Isabella points out, could it be possible for life to exist without liquid water, but with a different liquid instead?
Yeah, it's such a great question, and it always comes up at conferences, and people wonder if we're being too biased towards Earth because, all life on Earth needs liquid water, but that's only one data point. Life possibly only originated on Earth once, and that requirement there for liquid water, was there, and it's just propagated through for billions of years. There's been some speculation about things like liquid methane, and I think liquid ammonia is quite an interesting solvent. It has a reasonable range of temperatures that it can remain liquid over. I think both of them remain liquid over cooler temperatures compared to liquid water. And yeah, that's definitely a possibility. There's no way at the moment of really knowing if it's true until we were to say identify life which actually does operate off a liquid system that isn't water. So that's something for the future. I think at the moment it's all theory, and we won't really know until we start looking.
Absolutely. Of course. Thanks very much, Craig. Final question to you. If you've got any questions for all speakers, please drop them in the chat. I've got a few collected already. But final question to you, Craig. The names of these planets that you showed, there was a Kepler 186 and there was a Kepler 13. Where does this name Kepler come from?
Right. So many planets have been discovered with several different telescopes. Some are ground-based telescopes, some are space-based telescopes. Kepler was an astronomer who was alive hundreds of years ago, very famous, and they named a telescope after him recently, and that was about 10 years ago. The Kepler Space Telescope, I think, discovered something like 2,500 exoplanets. It's been our best telescope for discovery so far. And basically any planet that was discovered by the Kepler Space Telescope gets the name Kepler, and then it has the number that is assigned to the star, and then the first planet around that star will be given B, and then C, D, E, and so on.
So Kepler 186 was the 186th star around which they found a planet.
I'm not too sure on if it was the 186th star or if they designated in the catalogue the numbers of the stars, and then when they found a planet around it. But yeah, I'd have to check that one.
Fantastic. Well, thanks very much, Craig, for your interesting talk. I have a couple of general questions. At the first one, I think it probably would be Dr. Walsh who might be most appropriate, but I'm happy for everybody to. So the question came up. We're talking about rings and planets. So what happened with Saturn and the rings? Did Saturn form in exactly the same way as the stars that Martin and Katharine were talking about? And can we have life in these rings?
I think I'll take that one, Renee. Well, actually, all of the outer giant planets have rings. We can see Saturn's rings because they have a high content of ice, and that makes them very reflective. So we can see Saturn's rings very clearly because they reflect the light from the sun. But all 4 planets actually have ring systems. And if you're interested in this, look them up. They're actually really fascinating to look at. So yeah, so it kind of looks a little bit like a scaled down version of a star with a disk, right? And then what you're saying in the planetary ring systems is leftovers from the formation of the planet. And indeed, there's you can kind of think of the gas giant, there's a couple of different modes of gas giant formation, but in both cases, we do actually think that a disk will form. And it's the same physics that's going on, it's just happening on a much, much smaller scale than a star. You have rotation and you have gravity, and effectively that then pulls things kind of into this central object with a surrounding, what we would call a circumplanetary disk. So indeed, this is a feature that we see echoed in the ring systems in the gas giant planets.
Fantastic, thank you. The next question is actually from Martin, which, when we talk about telescopes and the biggest telescopes, what kind of computers have you been using to do your research, Martin? Do you do this on your home PC, or do you use supercomputers?
That's a very good question. Yeah, and it kind of taps into the I guess a hidden side of astronomers, because most people think of astronomers as working with really massive data with really big telescopes. Yeah, just looking up into the sky. But yeah, no, a lot of work is done using computer simulations, and so my work runs these really data intensive and memory intensive simulations that run on supercomputers. So this is not a computer that that just sits here in front of me. These are big stacks of machines that are in big centers together, and you can access them remotely, and you submit jobs, and then they run these big simulations that would take days, weeks, or even years to run on a little computer that can run in a couple of hours or days. Yeah.
Often computer science is part of astrophysics as well. Not only maths, also computer science. That's always good. I think, looking at the time, I may have time for 2 more questions. I believe that Isabella asked a question. I'm not 100% sure whether, I think either Craig or Katharine. And she must have noticed from the sketches that the rocky planets were always close to the stars and the giant planets further out. So is that always the case? Or can the gas giants orbit closer to the star and the rocky planets outside?
I could answer this, but I think probably Katharine would be better suited to that question.
Yeah, I mean, I can take that if you want. That's a really good question, because some of the exoplanets that we find are not like what we have in our solar system. I kind of hinted at that a little bit in my talk. Some of them are actually single planet systems where you have one hot Jupiter orbiting, like we call them hot Jupiters because they orbit really, really close to their parent star. And astronomers have been trying really hard to figure out if these single hot Jupiter systems do have planets on larger orbits. It's just that the planets on larger orbits are much, much harder to see. But it does appear that these seem to be single systems. And what we think happens in their formation is that perhaps that gas giant formed very early in the disk, when the disk was still present, and exchanged angular momentum with the disk in such a way that the planet then migrated inwards towards the star. And in the act of doing that, it may actually have impeded the formation of other types of planets there. So, for example, if there were rocky planets in the inner region, then interacting with a big Jupiter might have flung them actually out of the solar system, of their solar system. So we do have these weird types of systems. They're not very common. I think hot Jupiters have an incidence rate of about 1%, something like that. What is much more common are compact rocky planet systems like Greg actually described. So systems like the Trappist I, they're much more common than actually these weird hot Jupiters.
That's fantastic. Thank you. I'm just looking at the time. I think one very quick question. I think Greg might be able to answer that one, and short, because time flies. There was a question about the fact that Dr. Walsh mentioned collaborators a lot. And I think it's quite interesting to point it out that, contrary to what people might think, we're not really sitting alone on our desk. So, Greg, can you perhaps say a little bit about collaborations and doing science?
Yeah, so I started my PhD about 19 months ago now, back in October 2019. I'm working with Katharine, who's one of my supervisors, and then I also have a supervisor, Professor Dan Marsh in the US, who comes over to Leeds. Well, before the pandemic, he came over to Leeds. And we would work together to get me up to speed, because I didn't really know much at the start. I did my undergraduate degree, but it's amazing how specific you have to dive into a topic to get to a proficient level at research, and that's the whole point of the PhD, to become proficient. And so I've been working with 2 experts in the field, and then as the project progresses, we learn more about the work. Then we might want to pull expertise from the community. So this could be someone that we've worked with before, or who we've had a chat with at, say, a conference, be that an online conference or an in-person conference. It could even be someone who's in a different department at the university. So we're in the physics department. We might want some chemistry expertise or some engineering expertise if we're working on building a telescope. we could just go before the pandemic again and just chat to someone in another building. But now we obviously Zoom. And then finally, if you see someone's work who you think is it's good work and you think they're a talented scientist, then you might send them an email or ask to have a chat. And that's another way that collaboration can happen. And to be honest, these days, there's not many Einsteins left. There's no
well, we don't have that many Einsteins.
there's not, there's no single person doing it. It's big teams now, or small teams. Everyone really needs to pull expertise together to collaborate. And that's how science is done. It's becoming a lot more interdisciplinary now.
Fantastic. Well, thanks very much, Greg, for pointing that out. This brings the evening to a close, I'm afraid. I wanted to thank the three speakers tonight, Martin, Katharine, and Greg, for the fantastic presentations. If you enjoyed tonight's presentations, why don't you tweet us, let us know about it. And we also would like to have feedback on how you think it went. I believe that the link is on the bottom of the screen. This is the first time we had Be Curious LATES, so we'd love to hear what you thought. I hope you will enjoy the rest of the Be Curious events in the next 10 days as well. That leaves me with wishing you a very good evening indeed. Thank you very much.
Thanks.